In the last video, we discussed the fundamental theorem of line integrals, FTLI, and now it's time to put it to use. Okay, so just as a quick example, we're given a vector field, and we want to find the vector line integral over the curve that's presented below. And I should also mention that it would probably be nice if we had some direction. Let's just arbitrarily call that direction. Okay, well, I think if we look back at the fundamental theorem of line integrals, FTLI, we remember that this is going to be equivalent to or if we can find some a to b, and then we can do gradient of f dot ds for some scalar function, and certainly this curve meets those criteria, that it's going to be simple and and so we just need to figure out, okay, is f conservative? Is this true? Is gradient of f equal to vector f? Okay, and so I want you to pause the video and see if you can come up with a function f. So we want to find the existence of a function f such that if we look at the vector field, that's equal to the gradient of this scalar function. So pause the video and try and find that. Okay, well, I stared at it a while myself, and so I said f of x and y is equal to xy. I think that works. Okay, so by the existence of this, that means it's conservative, right? And so then we can say, okay, well, if it's conservative, it's path independent, right? That was a theorem. Okay, so it's path independent. So then we can use FTLI to say, oops, let's write that out, FTLI, this gives us that if we do the integral over path C of the gradient of this potential function f dot ds, we should be able to say that this is f of our starting point, 0, 1, minus f of 1, 0, our ending point. Okay, and I'm going to say, well, if you do this, you get 0. Okay, that's underwhelming. Okay, all right, so great. We've been able to solve the example using the fundamental theorem of line integrals. So really, this begs the question, well, how do we compute line integrals? And I'm talking about for vector fields. Okay, well, we certainly have the regular definition that we learned last time. Okay, we have that the line integral, so the integral over a curve C of f dot ds for a vector field capital F is going to equal the integral from a to b of f of x, and these are all vectors, x of t dotted with x prime of t, and that's a vector as well, and then dt. Okay, and then a and b are bounds of t. Okay, fine, great. We can use that definition. Okay, if we have a conservative vector field, then we actually get some more tools. And just a quick question is, how do we know if it's conservative? Well, that means that the vector field is equal to the gradient of some potential function f. Potential function that's a scalar. Okay, and so we certainly have the fundamental theorem of line integrals to solve this, but again, this does require some additional assumptions. .ds, namely, I believe we need that these are C1. Okay, and then this is going to equal f of b minus little f at a. Okay, and then another thing we can do is, if it's conservative, and certainly according to this, we can maybe try and find an easier path with the same start and end points, because we had that property that if f is conservative, it is path independent. So if we have the same start and end points, but we have an easier path, i.e. a line, that might help us. Okay. And so in this example, this a little bit more complicated than the previous vector field. Okay, C, we can see it's certainly simple. It's not self-intersecting. And we're just wondering if this vector field, or how we can find this vector line integral. Okay, well, regular definition. I need a parameterization. Okay, I'm stuck. Well, next thing I would try is I would look and see if f is conservative, so I need to find this potential function f such that, so I need to find the existence of a potential function such that the vector field is the gradient of this potential function. Okay, well, I don't know about you, but I'm going to encourage you to pause the video and take a little bit of time to look at this. Okay, well, is there this potential function? What I'm seeing is, well, there could be, maybe, because again, this gradient is equal to del x, or del f del x, and this is del f del y, right, by the definition of a gradient, but things aren't matching up yet, so I need a little bit more time to think about this. Okay, what I could try is, assuming it is conservative, I might try this last strategy, okay, and just pick an easier path. So, for example, I could go from, and I'll change my colors here, let's change this to green, I could go from this point to that point, and I forgot to mention that this is oriented in this direction. Okay, so I could just go that one simple straight line over. It's a different parameterization, and that will give me the same value if we have path independence, but I need that it's conservative first. So until I find this potential function, I am stuck. Okay, so we're going to have to pick up with that in the next video.